Let's talk about equal to 143 partition array for maximum sum. It gave us integer array AR and integer K. And we want to partition the array to the subarray for the length of at most K. And after partition, each subarray has their value changed to the maximum value of the subarray. So then let's return the largest sum after these partitions. So for example, this k equals 3, right? So we know if we partition this array into here, right? So we can change all of these three numbers to be 15. And from 9, we'll leave this 9 as size we want, size to be 1, right? And then the rest to be the next subarray will be 10, 10, 10. So that this sum is the largest. So how can we thinking about this question, right? Let's look at the length. It's 500 and the k is smaller or equal to this length. So means if we can do something like n square or n multiplied by k time complexity solution, we should be able to pass, right? So for this range, what we're thinking about is that we look at this in um, uh, every number in this array, right? So if there is a number array I coming, right? So this array I can belong to it must belong to some kind of partitions, right? So it so so we know this belongs to this partition, some kind of partition, and this partition can have the largest size to be k, right? Have this subarray large size to be k, and the smallest size for this partition is that this array itself, this array I itself is a subarray, right? So what we want is that we iterate this kind of width from 1 to k, trying to see what is the optimal sum when we coming out of an array I, right? So we think about this is some kind of DP problem, right? Because for all of the optimal sum in the previous indexes already calculate, right? So when we have a new array I coming, we just want to iterate the width from 1 to k, find what is the best largest sum when there is a new array I coming. So in this case, in the end, we just need to return dpn, right? And there is some kind of transition function we need to think about, right? So if this array I itself is a subarray, so that will be dp I minus 1 plus array I, right? What about if the width is 2, right? So we need to, because this 2 number, we need to change it to its max. So we can use a max variable here, right? So max variable will be max array I and array I minus 1, right? So that will be dp I minus 2 plus max multiplied by 2, right? And for the when we talk about dpi minus 3, do we need to compare these 3 variables one by one? We don't, right? Because we already have the max variable for the last 2. So we just need to compare the array I minus 2 with the max variable. So this max operation is just a O1 operation, right? And a multiple byte length, right? So we don't need to have compare all of the elements get its max one by one. So that's will get our solution just an O n k time complexity, right? So let's just write code for this. We're going to have int n equals array dot length, and we're going to have an actual index equals new int n plus one. The good thing is that it says that this number, they are all positive numbers, right? So we don't need to worry about the negative number. Actually, this question, if this negative number, I think it is also doable. But we do use the same way to write, right? So what we do is that we're going to we know we can write dp1 equals 0 and dp2 equals array1, right? But actually, this can also belong to the general cases. So what we can write is for int I equals 1, I smaller than n plus 1, I plus plus. So we're going to have, we can have a max equals 0. And if there is negative number, we have to use the max to be integer mean, right? And also we have dp this base we can also set as 0. Otherwise, if it's negative, we can set an integer minimum value, right? So what we do is that for we iterate the window size. Window equals 1, right? And the window should small equal to k. And also we need to make sure um this I minus window greater equal to 0, right? Because we we cannot get it out of bound, then window size increase the window size. So what we have is max equals max dot max and array I minus window size, right? And so our base equals max dot max base and dp I minus window size, the previous one, and also the max multiplied by window size, right? So we are going to have dp I will be equals best. In the end, what we want is to return dpn. It is a ON time complexity with the constant with the ON space complexity. We can also get this one as constant constant constant, right? So we can set result equals 0 because we'll find this n is only let me see. Actually, this we need at least W size, right? So we can change this to be an OW, right? To be W size, but you will see this W has the same OK. I mean OK, right? And then use a mod to save some space, right? But the thing is that this it has the same order with uh same order. It is also 10 to the power is 500 for k, right? So it will not save too much. So let's just keep this to be n plus 1. Um, we can also write Python code for this. So we are going to have n equals length array, and we're going to have dp equals this one multiplied by n plus 1, right? So what we do is that for I in range n plus 1, we're going to have max value equals 0, and the best equals 0, 0, right? Then what we do is for the window size in range from 1 to uh, k plus 1. So if I minus the window is smaller than 0, we should break, right? Then we are going to have max value equals max value and array I minus w, and our base equals max base and dp I minus w plus max value multiplied by w, right? And we're going to have dpi equals best. In the end, just return dp and